Hello and welcome back. In this module, we will explore the intricacies of container networking by deploying and exposing a containerized Apache server. This module is tailored to provide both theoretical knowledge and practical skills, ensuring you are well equipped to handle real-world scenarios. So let's get started. This module explores container networking with a focus on the differences between root and rootless containers and networks. It covers key concepts like network namespaces and exposes specific tools for managing rootless networks, such as Pasta and Netavark. Additionally, it provides insights into how Podman supports both root and rootless container networking, offering options for default and custom networks. Understanding the distinction between root and rootless containers is essential, especially for networking setup. There are two types of containers, root and rootless. Root containers run with root privileges, meaning they can do pretty much anything on your system. This is great for flexibility and control, but it's also a bit of a security risk. On the other hand, rootless containers don't have these elevated privileges, making them much safer but a bit more limited in what they can do. When a container is run as a root user, the processes inside it have root (UID 0) privileges. This means that both the root and non-root users inside the container are effectively mapped to the root user on the host system. While this setup allows for greater flexibility and control within the container, it also introduces significant security risks. If the container is compromised, an attacker could potentially gain root access to the host system, posing a severe threat to overall system security. When a container is run as a non-root user, the processes inside it operate with non-root privileges. This means that both root and non-root users inside the container are mapped to a non-root user on the host system. This setup significantly enhances security by reducing the risk of privilege escalation. Even if an attacker manages to compromise the container, they will not have root access to the host system, thereby limiting the potential damage and maintaining a higher level of overall system security. This overview delves into the critical differences between root and non-root containers within the context of containerization. It emphasizes the significance of understanding these distinctions for both security and functionality purposes. By exploring various container setups and associated commands, it sheds light on the implications and best practices for container deployment. The discussion begins with an examination of root containers operating on a root host. Container 1 exemplifies a typical root container scenario, where running as root grants full control but poses significant security risks. Conversely, Container 2 introduces the concept of running non-root processes within a root-owned container, offering a partial security improvement but still falling short of optimal security standards. Transitioning to a non-root host setup, the security landscape shifts significantly. Container 3 illustrates a safer approach where the container operates as root within, but the host denies root privileges. This configuration minimizes security risks compared to the root-on-root setup. Finally, Container 4 represents the pinnacle of security, with both host and container operating as non-root users, offering the highest level of security by mitigating privilege escalation risks. In essence, the overview underscores how the choice between root and non-root containers profoundly impacts the security and management of containerized applications. While root containers offer control, they also introduce significant security vulnerabilities. Conversely, non-root containers, especially on a non-root host, enhance security by minimizing the risk of privilege escalation and safeguarding the host system from potential attacks. Now, networking for these containers can also be either root or rootless. Root networks need root privileges to set up and manage, giving you full access to all network configurations and interfaces. This means they can do things like binding to low-numbered ports and interacting with all network namespaces. Rootless networks, however, don't require root access. This makes them more secure, but also a bit more limited in terms of what you can configure. Root network provides full control over network interfaces, allowing administrators to create and manage network namespaces, virtual interfaces, and other advanced network configurations. With root privileges, it is possible to manipulate all aspects of the network stack, including setting up custom routing tables, binding to privileged ports, and configuring firewall rules. This level of control is essential for complex networking setups and performance optimization, but comes with increased security risks, as any compromise could expose the entire host system to potential threats. Rootless networking operates with restricted control over network interfaces, prioritizing security by running without root privileges. In this setup, the container's network operations are limited to user space, meaning they can't directly modify network configurations or interfaces on the host. This restriction significantly reduces the risk of privilege escalation and enhances the overall security posture by ensuring that any potential compromise within the container does not affect the host system's critical network settings. To manage networking in a rootless environment, user space tools like Pasta or Slurp for Nets are utilized. These tools facilitate the creation and management of network namespaces and virtual interfaces without requiring root access. Pasta, for example, uses user and network namespaces to securely handle networking for containers, while Slurp for Nets provides user space NAT, network address translation, capabilities, enabling network connectivity for rootless containers. Although these tools offer fewer customization options compared to rootful networking, they provide a secure and practical solution for containerized applications that do not require extensive network privileges. Network namespaces are essential in containerization, providing isolated network environments for enhanced security and network management. The host network namespace contains vital components like the loopback interface for internal communication and the Ethernet interface connecting the host to the external network, along with routing and ARP tables directing and mapping network traffic. In contrast, pod namespaces isolate network resources for containers within a pod, facilitating seamless inter-container communication while ensuring isolation from the host network. This setup allows containers to operate effectively within their own network environment. Overall, network namespaces offer a robust framework for managing container networks by isolating network interfaces, routing tables, and ARP tables. This isolation ensures effective communication within pods while maintaining security boundaries between containers and the host system, crucial for secure, efficient, and scalable containerized environments. Rootless networking with Pasta offers a secure solution for container operations without root privileges, isolating network tasks from the host system. Pasta creates a network namespace in a rootless setup, allowing containers to communicate securely and efficiently without requiring elevated access. In the host network namespace, essential components like the loopback and Ethernet interfaces, along with routing and ARP tables, manage network traffic. Within the rootless network namespace set up by Pasta, each container operates independently, with its own network interfaces facilitating internal and external communication. For instance, Container 1 within the rootless namespace has its own loopback and Ethernet interfaces, ensuring secure communication within the container and with external networks. Pasta's rootless networking approach enhances container network management security by operating entirely within user space, eliminating the need for elevated privileges and reducing the risk of security breaches. This method ensures effective container management while maintaining robust security measures. Pasta is a valuable user space networking tool tailored for Linux users, aiming to tackle the challenge of connecting network namespaces and external hosts without needing elevated privileges or specific capabilities like CAP_net_admin. It achieves this by creating a tap interface accessible to processes within the namespace, similar to Slurp for Nets, and routing network traffic outside the namespace using native Layer 4 sockets. Unlike traditional approaches that implement a full TCP/IP stack, Pasta takes a more efficient route, coordinating TCP connection dynamics between sender and receiver and offering a fast bypass path for local connections. It also maps routing and addressing information to the namespace by default, eliminating the need for NAT. Pasta boasts support for various protocols like IPv4, IPv6, TCP, UDP, and ICMP/ICMPv6 Echo, along with defenses against sequence number attacks and features like window scaling. Security-wise, it ensures robustness by restricting dynamic memory allocation, disallowing root operations outside user namespaces, and employing restrictive SecOmp profiles. Pasta prioritizes performance with features like zero copy for local connections and generalized coalescing and batching for supported protocols. It interfaces seamlessly with Podman, offers native QEMU and libvirt support, and serves as a bug-to-bug compatible slurp for NET's replacement. Availability-wise, Pasta offers official packages for various Linux distributions and provides services such as a built-in ARP proxy, minimalistic DHCP server, and NDP proxy with router advertisements and SLAAC support. Overall, this slide offers a deep dive into Pasta's functionality, providing insight into how it addresses the complexities of container networking for rootless containers. Whether you're well-versed in networking or new to the field, it offers valuable information to explore or skim through at your own pace. When you launch a container without specifying a network, Pasta, a user space networking tool, creates it without any network setup. This configuration enables connectivity between the container and the host. However, when you start a container and specify a network, Netavark, another user space networking tool, creates it with a network interface on the specified network. This setup ensures connectivity between the container and the host. Netavark simplifies container networking, enabling you to run containers without requiring special access. Each container operates within its own space, facilitated by Netavark. It has its own connections, LO01 and ETH1, with ETH1 providing external connectivity using a unique address, container_IP. Designed in Rust, Netavark seamlessly integrates with container management tools like Podman, offering functionalities such as setting up container networks via configuration files, managing network interfaces, including advanced ones like Maclin, and handling firewall tasks like NAT and port forwarding. The default bridge network in Podman, named Podman, operates within the subnet 10.88.0.0/16. When Podman is executed with root privileges, this network is automatically utilized as the default option. It is equivalent to specifying the option Network Bridge or Network Podman explicitly. Users have the flexibility to modify the subnet assigned to this default network by adjusting the default_subnet parameter within the network section of the containers.conf5 configuration file. This allows for customization based on the availability of free subnets within the environment. Furthermore, users can rename the default network from Podman to any preferred name using the default_network key. It's important to note that these modifications take effect only when no containers are actively running, ensuring smooth transition and minimal disruption to container operations. Additionally, it's worth noting that the default network, by default, lacks DNS support. This deliberate choice is made for backward compatibility with Docker. For DNS support, users need to create a custom network, which we will explore in the next slide. Podman enables the customization of networks to address complex scenarios effectively. This feature proves valuable for establishing isolated networks tailored to specific groups of containers or for connecting containers across multiple hosts. Custom networks seamlessly integrate with DNS-based service discovery mechanisms. Unlike the default Podman network, custom networks benefit from having a DNS service provided by Advark, enhancing network functionality and service discovery capabilities. In this section, we'll explore practical commands for managing networks in Podman, covering tasks such as creating, listing, and removing networks, as well as connecting containers to networks. To create a network, you can use the command podman network create network_name. To list existing networks, use podman network ls. Removing a specific network is achieved with podman network rm network_name. To remove all unused networks at once, utilize podman network prune. Connecting a container to a network is done via podman network connect network_name container_name. Lastly, to create a container that is automatically connected to a specific network, use podman run network network_name. To expose containerized applications to the public, port forwarding becomes essential. This process entails mapping a port from the host machine to a port within the container. By doing so, external traffic directed to a specific port on the host is seamlessly redirected to the corresponding port within the container where the application resides. This enables external users or systems to access the services hosted within the container, allowing for efficient sharing of applications across networks while maintaining security and control over the communication channels. In this section, we'll cover essential commands for exposing applications to the public. To expose an application, use Podman run p-host_port container_port. To check the port mapping of a specific container, utilize Podman port container_name. For viewing port mappings of all containers, execute Podman port all. In this practical demonstration using Podman, we'll deploy an Apache web server by following a series of steps. First, we'll search for and pull the necessary Apache and UBI images. Then, we'll inspect the Apache image to ensure it meets our requirements. Next, we'll create a network to facilitate communication between containers. Afterward, we'll proceed to create Apache and UBI containers. To make the Apache server accessible to the public, we'll expose it using port forwarding. Following that, we'll validate the DNS and port forwarding setup to ensure proper functionality. Finally, once the demonstration is complete, we'll clean up the lab environment to remove any leftover resources. Through these steps, we'll showcase how to effectively deploy an Apache web server using Podman while maintaining best practices in container management. This slide showcases the lab diagram detailing all the containers and interfaces involved in deploying an Apache web server using Podman. The diagram illustrates the connections and interactions between the host machine, Apache container, client container, and various interfaces. It provides a visual representation of the networking setup, including port forwarding and DNS validation, essential for ensuring the proper functioning of the Apache server. In this lab demo, we'll start by exploring the world of container networking and port forwarding with Podman, a container management tool. This journey will help you understand how to manage containerized applications in a networked environment effectively. Let's dive in. First, we list the available database images for HTTPD by running the command podman search HTTPD head, which gives us the top results from the Podman registry. From this list, we choose the image registry.fedoraproject.org/f29/httpd. This image will serve as our Apache HTTP server. To pull this image locally, we use the command podman pull registry.fedoraproject.org/f29/httpd. Once the pull is complete, we verify its success by listing all available images with Podman images. Next, we need a client image to interact with our server. For this, we search for curl images using the command podman search curl head and select the image docker io/curl images/curl. This image provides the curl utility, which we'll use to send HTTP requests to our server. We pull this image using podman pull dockered io/curl images/curl and again verify the pull by listing our images with Podman images. With our images ready, we proceed to run the server container. We use the command podman run dit name server p8080:8080 registry.fedoraproject.org/f29/httpd to start the server container. The div flags are for detached, interactive, and TTY mode, respectively. The P8080:8080 part sets up port forwarding, mapping port 8080 on the host to port 8080 in the container. This setup allows external access to the containerized web server. To ensure the container is running, we check its status with Podman PS. Now that the server is up and running, we validate the DNS functionality within the default network by running the client container. We execute podman run name myclient dockerd io/curl images/curl meserver 8080, attempting to access the server using its container name. This step fails as expected because the default Podman network does not support DNS resolution. To understand this better, we inspect the default network settings with Podman Network ls and Podman Network inspect Podman. We observe that the default network, named Podman, has DNS disabled. This explains why the container name could not be resolved. To enable DNS, we create a new network with DNS support using the command podman network, create network, subnet 192.168.1.0/24, gateway 192.168.1.254. This command sets up a new network named network with a specified subnet and gateway. We verify the creation of this network and inspect its settings using Podman Network ls and Podman Network inspect network. We confirm that DNS is indeed enabled in this new network. Next, we remove the existing server and client containers using Podman Container RM Meserver F and Podman Container RM myclient F. We then rerun these containers within the new network. The commands are podman run dit name meserver network network p8080:8080 registry.fedoraproject.org/f29/httpd for the server, and podman run name myclient network dockerd io/curl images/curl meserver 8080 head for the client. This time, the server name resolves successfully. We run curl localhost 8080 head. This command sends a request to the local host's port 8080, which is forwarded to the server container's port 8080, confirming that our setup is correct. Finally, we clean up our environment by removing the containers and images, ensuring no leftover resources. Remember, always leave your environment cleaner than you found it, unlike your room, where chaos reigns supreme. And there you have it, a complete walkthrough of setting up, testing, and cleaning up a containerized Apache server and client using Podman. This process not only demonstrates container networking and port forwarding, but also emphasizes the importance of environment management in containerized applications. Happy containerizing! In the next module, we will explore how to manage persistent data in Podman containers, ensuring that data persists even if containers are removed. Sounds fun, right? See you soon.